All right, today we're going to finish chapter 20, and then Tuesday and Wednesday we're going to review for the test on Thursday. All right, so let's go to the previous slide. So we went through this last time. If you have a high mass, so if your mass is too large, you can tell that by the periodic table. The example was carbon 14. All right, so carbon 14, carbon should have a molar mass of 6 from the periodic table. So that is a high mass isotope, higher than the periodic table's molar mass. So when you have that, you predict a beta emission. So you have to know that a beta is a 0 minus 1, or you can show it as an E, 0 minus 1, either way. All right, so then you have to know that if you have 14 on the top, you got to have 14 on the top on the other side. When you got 6 on this side, you got a minus 1 on this side. You have to have a 7. So 7 minus 1 is 6. Then the periodic table, you know that is the atomic number. 7 is the atomic number for nitrogen. All right, so then you look at the periodic table and you look at nitrogen's molar mass. It's 14, so it's going to a more stable nuclei. If you have a low mass isotope, you have two choices. You can do a positron emission or an electron capture, and those will give the same product. So if we stick with carbon and we go with carbon 11, all right, so now we look at the periodic table. It's supposed to be 12. Now it is less than the periodic table. It's a low mass isotope. And so now it's going to do a positron emission. All right, and so that I will put as a beta and then a 0 and a plus 1. All right, and so then your numbers on top, you got 11. On bottom, you've got a 5 because 5 plus 1 is 6. And you see that is boron. You go to the periodic table and you see that boron's molar mass is 10.8. So that would be predicted to be a stable isotope for your boron. And if you don't believe me, do an electron capture of that. You're going to get the same thing. So remember that capture means a reactant. So an electron capture, 0 minus 1. All right, so capture means reactant. So then you have 11 on top, and then 6 minus 1 is 5 on the bottom. All right, so you get the exact same nucleus. You get a boron 11 in either case, a boron 11. All right, so when we go to the next page, and it says, what is the predicted type of radioactive decay for calcium 47? You go to the periodic table, you know it's atomic number 20, so you can go right to it without looking for it. And you see the molar mass of calcium is 40. All right, and so you find your molar mass, and it is 40.08. All right, and so now you compare that to the isotope 47. So you have a high mass isotope. For your calcium, and so that is going to undergo a beta emission. So 0 minus 1, and then so on top you've got your 47, on bottom you've got your 21. 21 minus 1 is 20, and then you see that is Sc. All right, and so the molar mass of that is about 45. So again, we're getting much closer. This one was too high by 7. Now it's only too high for Sc by 2. All right, so that is your expected type of radioactive decay. High mass, beta emission. Low mass, positron emission, or electron capture. Anything that has an atomic number greater than 83, you predict an alpha emission. We are not going to be tested over the radioactive decay series, so if there are any questions on those, they will not be on the test. All right. So you have two samples of water. One's made up of the 99% of hydrogen, which is the H11. All right, so that is 99% of all hydrogen is the 1 and the 1. It's 99 plus percent. 99 probably rounds to 100%. I think it does. All right, so very, very small percentages you will find an isotope of hydrogen with a 2 and a 1. And this is deuterium. As a particle is a deuteron. Right? So it is a deuterium or a deuteron. And if you have heavy water, they're not using heavy water. Heavy water is D2O, is how they would write it. All right, so that's heavy water. Because deuteron is twice the mass as the regular hydrogen. So they call that heavy water. Deuterons are used, deuterium is used in chemical reactions as well as the nuclear reactions. Now, your tritium, which is your H31, I have never seen that used in regular chemical reactions. This is, for as far as I know, only used in nuclear reactions. This is tritium. Easy to remember, tricycle, 3 wheels, mass is 3. A deuce, deuteron, 2, all right, so that's a mass of 2. And then this is just a regular, it would be a proton as a particle. It is just the regular hydrogen mass. All right, so your heavy water and your water will react similarly, so you can actually, you label your hydrogen as an H21, so D is equal to H21, D, so a D2O, the D is equal to an H21. All right, and so you can label your hydrogen. So if you're doing a mechanism, you don't want to know where the hydrogen's coming from, you can use heavy water and see where that deuterium ends up. All right, so would you expect the 2 water samples to be chemically similar? They should react very similarly. Physically the same? No, they're not physically the same. Your 3,1 is going to have a much larger mass than your 1,1 hydrogen. All right, and which one of these would you expect to be radioactive? Well, tritium and deuterium, these are your radioactive isotopes for your hydrogen. The regular H11 is not radioactive. All right, transmutation. So we are going to change one element into another. All right, so we're going to do what's called a transmutation. This is a nuclear bombardment reaction. So we're going to take a nucleus, we are going to bombard it with a very fast particle coming in, and then it's going to release a new nuclei and another particle. So in this example, we have our target is our nitrogen 14. All right, so that's our target. We're going to put in the cyclotron, it's a particle accelerator, helium. We're going to hit our nucleus with a helium 4-2. All right, and so then they have to give us something else. Most common is they'll say it kicks out a proton. All right, and so you can put P11 or you can put H11. It doesn't matter here. You can put P11 as well as an H11. All right, normally they do not give you your product nuclei. So here's the target. You hit it with the alpha particle, you kick out a proton, and you get your product nuclei. And so again, it's very simple math. You got 18 on the top here. You got 1. You need 17. On the bottom here, you got a 7 and a 2. That's 9. Here you got 1. You need 8 more to get 9. You go to the periodic table. You see that atomic number 8 is oxygen. All right, so they're not going to give you the whole reaction. There's going to be one missing thing. You're either going to be missing a particle or one of the 2 nuclei. But 3 of these have to be given in order for you to balance the reaction. You also have to know how to do the notation. The notation here is going to be your target nuclei, a nitrogen 14-7, and then in parentheses you have the bombarding particle, so you're going to bombard that with an alpha particle, and then a comma, and then you have the ejected particle, And these are always in symbol form. So you have to know that alpha is a helium-4, 2. You have to know P is proton, that is an H11, or you can put P11. You just have to know they are 1, 1. And then, usually that's the question, they'll put it like that and say, what is our product nucleus? And so then you would write the reaction, just like we started up here. So here's your target, there's your incoming particle, and here's a ejected particle, and then you would then just add the numbers on the top on both sides to get your 17 and get your 8. Periodic table, you have your O. So then you would finish your notation. So then your notation is oxygen 17, 8. All right. So here is another bombardment reaction. You have beryllium 9, 4 being bombarded with alpha particles, and it's kicking out a neutron and a carbon-12 nucleus. And so the notation, well, again, you got your 9 and your 4 is 13, which is equal to 12 and 1, 13. You got your 4 and your 2, that is 6. You got your 6 and your 0, that is 6. So the notation is your target molecule, beryllium 9, 4, is bombarded again here with alpha particles, and it's ejecting a neutron, and then the product nuclei is a carbon 12 and 6. So that is the notation for that one. For the one down here, again, the bombarding particle does not have to be alpha, although our first examples, all three of them are an alpha, and that is the bombarding particle. So aluminum 2713 bombarded with an alpha particle, kicks out again a neutron, and then the product nuclei is your phosphorus 30. So again, you got 27 and 4 on top, 31. That's 30 plus 1, 31. You got 13 and 2, 15. You got 15 and 0, you got 15. So again, the top numbers, bottom numbers have to be the same. Your phosphorus 30 is a low mass isotope. If you look, well, it's barely low mass, but P is P31. So again, it is a slightly low mass isotope. And so the predicted decay mode would be a positron emission, or the same thing would be an electron capture. In either case, and this one is showing a positron emission, that you get a silicon 30 as your product. So this is not a transmutation reaction. This is a radioactive decay mode. That is a beta emission. The only time we have a transmutation, turning one element into another, is when you have an incoming particle and an exiting particle. All right, and so here they're showing how you would do the notation. So we went through the notation. You have to know all the symbols for all of the different particles. All right, so there's a few here. They have the deuteron, but they didn't put the tritiron. So that is an H31, and that is a lowercase t. You've got your gamma. You got to know gamma. All right, so that is gamma, and that is the symbol for gamma. So also you have to know the numbers. That's very important. Gamma is pure energy, so that's 0, 0. Neutron is 1, 0. Proton is 1, 1. Deuteron is 2, 1. And, well, that's listed right over here. And then your alpha particle is a helium, and that is a 4, 2. You should not write alpha 4, 2. You should always write helium 4, 2. All right. I know there's other ones missing here. Let's see. Of course, electron. So an electron is just E minus. So that is a 0 minus 1. So make sure you know electron, 0 minus 1. That's also a beta particle, 0 minus 1. If you have a positron, I didn't list that one today. So that is a E 0, 1, or this is electron. So this is electron or beta particle. It should be or. So it can be called either one, beta emission or electron emission. Usually it's called beta emission. Positron emission. All right, so positron emission is that or a beta, 0 and 1. All right, so you have to know all the different symbols and what numbers go with those symbols in order to get these bombardment reactions correct. All right, so here they just want you to write the notation. I think we've already done this one. Yep, we did this one already. Be94, and then we had alpha, the incoming particle, neutron, ejected particle, product nucleus, 12, 6 carbon. And this one, normally when these are asked as questions, there's one thing missing. Not all 4 things are given. All right, so you write the reaction here, aluminum, 2713, plus a proton. You can write P11. I'm going to write H11. And then a deuteron, which is a 2,1 hydrogen. And then that gives, and usually that's where the answer to that is not already given. So you would have your 27 plus 1 is 28. On the left, on top, you only have 2. So, of course, you need a 26 to get the 28. On the left, you got a 13 and 1, that's 14. And so that's a 1, so you still need 13. And so it's still aluminum. And so you just get a different isotope of aluminum. You have the same number of protons, but a different number of neutrons. All right, so in order to get that particle enough energy to come in and bombard your product or your target to get your product nuclei is you need to have a particle accelerator. All right, and so it makes these things go at very high speed so you can do a bombardment reaction. All right, and that accelerator, particle accelerator, is called a cyclotron. And here's a picture of a cyclotron. There's going to be questions on what does a cyclotron look like, but there it is. It's make the particle go fast, speeding it up, and it's going to hit your target material right there. And it's going to kick out a particle and give a product nuclei. All right, transuranium, that is a very easy definition. It's all of your elements past uranium. All right, so, and all of those have a greater than 83, because it's greater than 92 when they're transuranium, and so they will decay by a alpha emission. There may be other decay modes that they go by, but they all will go by an alpha emission. When you are predicting anything greater than an 83 for your atomic number, you're predicting a alpha emission. All right, so we're going to start doing some fission and fusion. All right, so what happens here is that you have your uranium doing a neutron capture. So again, it is called a capture if you are a reactant. So here we have a neutron capture. So uranium-238 goes to uranium-239. Then your uranium-239 would then undergo a beta emission. And so this is showing a beta emission product. All right. So again, you're not going to predict these things. Well, you can predict the last one a little, but not really. Again, uranium-238, the predicted mode, it's greater than 83. We are going to predict an alpha emission. So when it's not predicted, then you have to be given 2 things. There can only be one thing missing. And again, the numbers on top have to be the same on both sides. The numbers on bottom have to be the same on both sides. All right, here's uranium-238 reacting with a deuteron. All right, so that would give you, if it was one product, 240 and 93. It is not one product. They would give you a product. And so here's 93 and 238. And so what you would end up with is a 2, 0. but you don't know what a 2-0 is because 2-0 doesn't exist. When you have 2-0, that means you have 2 neutrons and no protons. And that is exactly what you have. 2 neutrons and no protons. So you have your 2 neutrons. Sometimes that messes people up. You may want to get rid of the coefficient and actually write it 2 times, so that you know that you have 2 of these particles, 2 of these neutrons, so that you have your 240 on top and you have your 93 on bottom. And then the last one here is just a decay mode. It's just doing a beta emission. All right, again, 238. Yes, 238. 93. Here is 94 minus 1, which is 93. So again, make sure these are very simple math questions. Make sure your number on top on both sides are the same. Number on bottom on both sides are the same. All right, so plutonium, 239. All right, that's 94. Okay, so Pu, 94, 239. Bombarded by alpha particles plus helium, 42. All right. It emitted 1 neutron, N, 1, 0. What is the product nucleus? So from that and a periodic table, you get plutonium, which is number 94, element 94. All right, so that's 239. That is the mass. Plutonium 239 is the mass of plutonium 239. All right, 1 alpha particle, 4 2s. So now we have a 243 on the top. So this is 243 when you add 239 plus 4. And so this one has to add up to 243. We have 1, so we need 242. 242 plus 1 is 243. All right, on bottom, we got 94 plus 2, that's 96. We have 0, we need 96. We look at the periodic table, and 96 is Cm. So you just find that's the atomic number, and you find it on the periodic table. That is Cm. And so there is your reaction, and this is a bombardment reaction, and so you have a notation. Pu, 239, 94. Incoming particle is your alpha particle. The ejected particle is your neutron. The product nucleus is Cm, 242 and 96. All right. We're going to start doing some kinetics here. We're going to look at first order kinetics. All of our nuclear reactions that are undergoing decay modes, these are all first order kinetics. All right, and so we know that our K units is going to be 1 over time, usually seconds, but when you're doing half-lives that are in the years, we don't really go in seconds, and we kind of go in years. It doesn't matter. It has to be 1 over a unit of time. All right, and so we have our half-life, 0.693 over K, and we have our rate is equal to K times the nuclei at time t. And we have our integrated rate law. So these are all from chapter 13. Integrated rate law is going to be your rate, integrated. It's going to be the ln of n at time t over n initial. So nuclei at time t, nuclei that we started with. That's equal to negative kt. All right, so this is all first order. We don't have to worry about is it first order, is it second order, what order is it? Always it's going to be first order for nuclear reactions. All right, so we can then look at the activity. This rate is also called the activity. All right, and we will detect this activity using a Geiger counter. So this is a instrument that detects radioactive nuclei. That one I'm not as familiar with. All right, so we have our activity. Just like when we have Avogadro's number for moles, we're going to have activity in terms of a Curie. So Madame Curie has a unit named after her, and that is a 3.700 times 10 to the 10th nuclei disintegrations per second. So here is where the unit of time is going to matter, because this unit is in nuclei disintegrations per second. So that's, again, when you have to be in seconds for your unit of time in order to convert to a Curie. And that is called its activity, the number of Curies. We're not going to talk about your if you're working with nuclear in a nuclear power plant, you're going to have some pen they're going to stick in your pocket. It's going to detect all the different radiations that you have during a day, during a week, during a month, and they will not let you be overexposed to nuclear radiation. All right, and so there aren't going to be any test questions over how much radiation that you can have in a day, in a week, and a year. All right, so rate of radioactive decay. Again, this is first order rate law. Rate is equal to K times the number of nuclei. So again, number of radioactive nuclei. That is your N at time t. That is your number of radioactive nuclei at that time. K is a constant. It's the rate constant. But when we're looking at nuclear radiation, so it's a radioactive decay. All right, and so your rate constant is the radioactive decay constant. We're doing radioactive nuclear reactions. All right, and so again, we're going to find half-life. Half-life is 0.693 over K. We could solve for K and say that, of course, multiply both sides by K, divide both sides by your half-life. So that's 0.693 divided by T1/2. So you can find the half-life if you're given K. You can find K if you're given half-life. It does not depend on the initial concentration. Second order would depend on initial concentration. First order does not. All right, so we have a 1 milligram sample of technetium-99. It has an activity of 1.7 times 10 to the minus 5 curies. Decaying by beta emission. What is your decay constant? All right, so rate is equal to N at time t. So K times your nuclei at time t. So they give us the rate. The rate is your activity. All right, so when you see activity, that is also your rate. All right, and so your rate or your activity is 1.7 times 10 to the minus 5 curies. All right, and you have 3.700 times 10 to the 10th disintegrations per second. So 1 curie, put that on the wrong side. 1 curie is 3.700 times 10 to the 10th disintegrations per second. So the Curie cancels the Curie, and now you have your activity in disintegrations, nuclei disintegrations per second. All right, and so that is your rate. That goes right here. That is your rate, nuclei disintegrations per second. All right, now we can find our number of nuclei because they tell us that we have a 1 milligram sample. So you have your 1.0 instead of m, I'm putting times 10 to the minus 3 grams, because milli is 10 to the minus 3. Technetium 99, you don't have to look up the mass of that. That is an isotope that has a mass of 99 grams per mole. All right, and then we want the number of nuclei. So we have Avogadro's number. We have 6.022 times 10 to the 23rd nuclei per mole. All right, and so that is how you find your number of nuclei at time t. All right, and so then we have our n at time t. And so the question was, what is your decay constant? You simply take your rate, divide by your nt, and you have your decay constant k. And so when you get that, you take, when you multiplied your 1.7 times 10 to the minus 5 times your 3.7 times 10 to the 10th, here is your activity or your rate. And that is 6.3 times 10 to the 5th nuclei disintegrations per second. And then when you had your 1 times 10 to minus 3 grams of technetium 99, the molar mass was 99. And then multiplied that by Avogadro's number, you get your number of nuclei to be 6.1 times 10 to the 18th technetium 99 nuclei. All right, and so when we divide that, so we take our equation, and that is your rate is equal to k, and t, divide both sides by number of nuclei at time t, and that cancels, so you're taking your rate and you're dividing by your 6.1 times 10 to the 18th. So the nuclei cancel the nuclei, and you have k in units of per second. And that number is 1.0 times 10 to the minus 13, 1 over second. That is your decay constant k. All right, once you have your k, you can easily find your half-life, because your half-life is equal to 0.693 divided by k. All right, so if we do that, we have a half-life, but this is a half-life in terms of seconds. It's going to be a giant number. No, I don't need a calculator to get that number. So you have 0.693 divided by 1.0 times 10 to the minus 13. Bring that up. It's positive 13. And so you have a 6.93 times 10 to the 12th. And that is your half-life in seconds. All right, so you just take your 0.693, divide by your k, and then you have your half-life. All right, so whatever units you have for k, 1 over seconds, those time units will be the time units that you also have for your half-life. They must match. Your k time units, your t1 half time units must be the same unit. It doesn't matter which one it is, but it has to be the same units. In this case, it is seconds. All right, so they're going to work it out for you. They're going to put that on here and get your number. All right, so again, the question would probably ask not in seconds, because when you look at 6.9 times 10 to 12 seconds, you really have no idea how long that is. So many times you're going to have to convert to years, right? So you take your seconds, and you know that there are 60 seconds in a minute. You know there's 60 minutes in an hour, 24 hours in a day, 365 days in a year. And now you have your half-life in years. And so it is 2.2 times 10 to the 5th years. So you're talking 220,000 years before half of this is going to be gone. Many of these radioactive isotopes have very, very long half-lives, which is a problem, because we have a lot of nuclear waste. We don't know what to do with it. We bury it in the ground, and we think it's going to last for 220,000 years. We don't have history that goes that long, so we have no idea what's going to happen to that container over that many years. So that's why we kind of stopped doing any new nuclear power plants, because we don't know what to do with the waste. All right. All right, tritium, radioactive nucleus of hydrogen. All right, you got a half-life of 12.3 years. What is the decay constant in seconds? Okay, so you can't just get K, which is equal to 0.693 over your T 1/2. Well, if it said what is the decay constant in 1 over years, you simply put the 12.3 in, but it wants 1 over seconds. So first you need to convert your 12.3 years into seconds. So now you have 365 days in a year, 365 days in 1 year. You have 24 hours in 1 day. You have 60 minutes in 1 hour. And you have 60 seconds in 1 minute. And so you got to multiply that by 365, then multiply it by 24, then multiply it by 60, then multiply it by 60 again. Once you have that number, so once you have your units changed to seconds, then you can plug that in to the 0.693 over T 1/2, and that will give you your decay constant in 1 over seconds. All right, so when you multiply all those, you get 3.88 times 10 to the 8th seconds. So you plug that in, 0.693 over 3.88 times 10 to the 8th seconds. And now here is your K value in the units that they asked for, 1 over seconds. So you got 1.79 times 10 to the minus 9. 1 over seconds for your K value in the units of per second. So make sure if it doesn't say what the units have to be in, they can be in any units. But be careful, many times it says have the units in seconds. All right. Let's see what the other part of the question was. All right, so that was the decay constant in 1 over seconds. Now it says what is the activity? Remember, that is your rate in curies. All right, so there again, here it's per second, so it's specific what units you have to be in. Here it's in curies. Again, it is specific on your units. So you will be given what a curie is. So on your sheet, you'll have a curie, and it'll say 3.700 times 10 to the 10th disintegrations per second. I think it might say nuclear disintegrations per second. So your nuclei are disintegrating per second. That is what it's meant by disintegrations per second. All right, and so the key here is that's why the K value was required to be in seconds, because part B, if this didn't say and you put it in years, that's fine. But then when you come down here and your curie is per second, then you've got to convert whatever units you had up here into seconds. All right, and we have 2.5 micrograms of tritium. So you have to have a 2.5, you have to know micro is times 10 to the minus 6 grams, and tritium has a mass of 3. And so you divide that by 3 grams per mole. All right, and so then you have Avogadro's number, 6.022 times 10 to the 23rd nuclei per mole. And so now you have your N at time t. All right, so you have your rate is equal to K N T. All right, we already have our rate constant K in the right units. We found that right here. First thing we did, we found our K value. Now we have our N at time t, all right, and that's going to be in nuclei. All right, so then it's going to say that's going to give us our activity, in nuclei per second. So when we multiply those together, all right, so we have our rate is equal to K, and at time t, again, you have your micrograms. You got your mass for H3, which is 3 grams per mole. You got Avogadro's number. So here is your number of nuclei. That is your NT. All right. And so now we have our K value in per seconds, and we have our nuclei. And so we multiply those two numbers. And now we have 9 times 10 to the 8th nuclei per second. And that's what we have to have because it asks for the rate in curies. And so we have 1 curie is 3.70 times 10 to the 10th nuclei disintegrations per second. And your nuclei disintegrations per second cancel nuclei disintegrations per second. It is per second. You had to have your K value here in per second in order to convert your rate into curies. So when you divide those numbers, you get 0.024 curies. Right? And so anytime you have curies, that is a rate, that is an activity. All right, so your activity is the same as your rate. If they ask for an activity, you are solving for rate. If they want it in curies, you have to convert it into curies. You'll have your answer for your rate in nuclei per second in order to convert it to curies, which has the units of nuclei per second per curie, 3.7 times 10 to the 10th nuclei per second. All right, now we're going to do the integrated rate law. So we had our rate, then we integrated it, and we did the integration for your first order, and that was the ln of A at time t over concentration of A initial, that was equal to negative KT. Now we are not doing a chemical reaction, we're doing a nuclear reaction, and so we're going to look at the nuclei. And so it is the nuclei at time t over the initial number of nuclei is equal to negative KT. All right, and so this is your integrated rate law for your nuclear reactions. They are all first order. All right. Original number nuclei, nuclei time t. And of course, if they ask for the fraction of nuclei remaining, that is your NT over your NO. All right, so that's a very common question. What is the fraction of nuclei remaining after some period of time? Or if they want a percent, multiply it by 100 and you'll get percent. The number of nuclei original is always a bigger number because they are always undergoing radioactive decay. All right, so here's an example of phosphorus 32. Radioactive isotope, half-life is 14.3 days. A biochemist has a vial containing a compound of phosphorus 32. If the compound is used in an experiment, 5.5 days after the compound was prepared, what fraction, so now we're looking at our NT over NO, what fraction of the radioactive isotope originally present would remain? All right, and so then it says, suppose the sample is 0.28 grams. How many grams would remain after 5.5 days? So here you just take your ln, n at time t, over n initial, and that is your answer. That's the fraction. This is the fraction that we're looking for, is equal to negative kt. Now, again, the only thing that has to be true, you can convert everything to seconds. That would be a waste of a lot of time. The only thing you have to be sure of is that your K value and your T value have the same units. Here is days and here is days. Yes, so our unit of time is days. All right, they have to have the same unit of time. All right, so of course this is your half-life, but you know that your half-life, T1/2, is equal to 0.693 over K. And so if you solve for K, that is 0.693 over T1/2. So you can rearrange this by, instead of putting in K, you can put in 0.693 over T1/2. So that's equal to negative 0.693 over T1/2 times your time. All right, so if you want to replace your K, so that's just the substitution, 0.693 over T1/2. Here's K, that's what it's equal to. You can plug that in. And so now you see when you put in your 14.3 days for your half-life, 14.3 days, and you put in your time at 5.5 days, you see that days will cancel days. Right? So that's the key. They have to have the same time unit. All right, so you get that number, then you push your e to the x button to get your fraction that remains. Okay, so t, all right, 0.693. T, okay, all right, good. So then they put in their numbers and then they push the buttons. You get a negative 0.267. So when you put this in, you get a negative 0.267. Then you push your e to the x button. And so e to the negative 0.267 is your fraction, which is your answer. All right, and so you have your fraction of nuclei remaining is a 0.77. Percent of nuclei remaining, 77%. All right, but then we started with 0.28 grams. All right, so since we started with 0.28 grams and only 0.77 remains, so you simply take your 0.28 times your 0.77, or you can leave that whole number in your calculator, and that will give you a 0.21 gram sample remains. So you bought 0.28 grams, and then 5.5 days later, you only have 0.21 grams remaining. All right, because only 77%, only the fraction 0.77 remains after 5.5 days. All right, so when you are doing these in the hospital, you have radioactive tracers. If your half-life is in days, you can't order it weeks ahead of time. You got to pretty much get it that day. If it's minutes, you got to basically make it right on site. So it really depends on the half-life of the radioactive tracer. You don't want things that have half-lives of years because then they're in your system forever. You want them to be half-lives of days, minutes, probably not seconds. That's way too fast because then their concentration decreases to essentially zero, but never zero. All right, radioactive dating, we use carbon-14. Carbon-14 has a half-life of 5,730 years. All right, so while you are living, a plant or animal is living, the fraction of carbon-14 remains constant due to exchange with the atmosphere. All right, once an organism is dead, now it's not breathing, now it's not getting any new carbon-14. All the carbon-14 is just undergoing your beta decay, and so your carbon-14 amounts are going to go down in a predictable amount, predictable in how old that the organic compound is. All right, so you can measure how old a plant or an animal is by doing your carbon-14 dating. All right, so a piece of charcoal from a tree killed by volcanic eruption that formed a crater in Oregon. It has 7.0 disintegrations of carbon-14 nuclei per minute per gram of carbon. All right, present day carbon, all right, so living matter, it gives 15.3 disintegrations per minute per gram of total carbon. And so this is your ln of n at time t over n initial. That's equal to negative kt. All right, and so we see now our activity here, our nuclei disintegrations per gram of carbon. That is 7. And so you have your ln of 7.0, what it is now, to what it was originally, 15.3. That's equal to negative, okay, so instead of k, we're going to have 0.693 over t1 half. So we have 0.693 over t1 half, which is 5,730 years. And then you have your time, and that's what we're solving for. How old is this tree? All right, so you take your 7 divided by 15.3, you push the ln of that number. So you may want to put that in parentheses, ln of that division. All right, then you have to take the negative 1 on both sides, multiply by 5,730, divide both sides by 0.693, and you have your time. And so we know for sure that the ln of 7 divided by 15.3 is going to be a negative number because you can never have a negative time. So that's a negative number, that's a negative number. You have your positive number. And of course, since I put in years for my half-life, my time units are going to be in years. This is, all right, I don't know why they do this, but anyway, all right, so the ln n a time t over initial is equal to negative kt. If you take the negative of both sides, you have the negative ln of n at time t over n initial is equal to kt. What they have done is they have inverted. When you have a negative, you can invert your fraction because this is the ln of n at time t minus the ln of n at time 0 initial. And so they have gone to a different equation, taking the ln of the initial over n at time t, and that's equal to kt. Not sure why they would do it. I would leave all of my answers in the equation in this form. But for some reason, they have decided to do it this way. All right, so if you do it, doesn't matter which way you do it, I would highly recommend putting it in this equation, the one that's going to be given. And what you find out is you're going to get your answer in years, and that is a 6.5 times 10 to the third years, or 6,500 years old. And so that tree was 6,500 years old. So since we know that, and we know it was killed in the volcanic eruption, we can now predict the date of the volcanic eruption. So if that's many years ago, and today is 2021, and we do sig figs, we see that this eruption occurred at 4,500 BC. And of course, your error is in this 5. So that's plus or minus 100 years. All right. So that is 4,500 BC or 4,400, 4,600. All right. So it's about in that error. We have our sig figs that tell us that we're confident to the hundreds. All right, so once you get too old, when you have many, many half-lives of carbon, there's essentially no carbon left to detect. And so when things are really old, we have to have a different method for determining how old something is. All right, so radioactive tracer. So you have a small amount of an isotope that you can inject, you can swallow, whatever, and then they can follow and find a bunch of different things. This is used in medicine. So more than 100 different radioactive isotopes have been used in medicine. All right. So, but you have to really be careful of those half-lives. You want them to be small, but not so small that you are 5 minutes late and now it's gone. So, all right. Energy of nuclear reactions are tremendous amounts of energy. All right. So you have your chemical reaction. In a chemical reaction, we have what is called a conservation of mass. It is not a real conservation of mass, but the mass is such a small amount that we have what is called a conservation of mass. All right, but Einstein's equation tells us that if we're getting energy from a reaction, that is also going to, if we have a energy released, negative energy, we have lost mass. All right, so we have any change in energy is going to be a change in mass. All right, so if we have lost mass in a reaction, then we have released some energy. All right, and so when you have so it's such a small amount in a chemical reaction that we say we have a conservation of mass. We could never detect it in our labs, at least not in our labs here. However, nuclear reactions have a lot more energy, which means they have a lot more loss of mass, and so you can actually detect the mass loss in a nuclear reaction. All right, so we're going to have our table 20.3. All right, so it has elements. All right, interesting that it is elements. Elements and particles. All right, so if you want the mass of an electron, you use that number. If you want a mass of a neutron, you use this number. If you want the mass of a proton, you use this number. Now note that we said that H11 is the same as a proton, 1,1. But you look at these two masses. Those two masses, this one and this one, these two masses, the mass for the proton is 1.00728. The mass of a H11 is a 1.00783. It has a larger mass because this is the mass of an element. So this hydrogen, H11, as an element has 1 proton, 0 neutrons, and 1 electron. So it's not H plus, it's not an ion. All right, and so this has the mass of the electron. So to get the mass of a hydrogen nucleus, the nucleus only contains the protons and neutrons, you have to subtract 1 electron. So here's the mass of an electron. So if you take this number and subtract 0.000549, you get 1.00728. Well, maybe that's not true, but anyway, that's going to be very close. There's always sig fig problems as well. But all of these have an electron in it. When this is a 1 and this is an element, that all has 1 electron in it. So to get the nuclear mass, you've got to subtract 1 electron from all of these. Now when you get to the helium, so if you wanted the mass of an alpha particle, it is not 4.00260. That is the mass of the helium element, that is 4.2. That includes 2 electrons. So you would have to subtract 2 electrons to get the nuclear mass of a helium particle. That is an alpha particle, a helium 4.2. You'd have to subtract 2 electrons here. This one, here are 2 isotopes of lithium to get the nuclear mass. Subtract 3 electrons. Subtract 3 electrons. Electron mass will always be given. All right, here we're going to have to subtract 4 electrons. Here we subtract 5 electrons. All right, so you get the idea. So when you're talking about the element has neutral element, and so it has the mass of the electrons in it. When we're doing nuclear reactions, we only want the mass of the nucleus. We do not want the mass outside the nucleus. Outside the nucleus is where your electrons are at. All right, so you'll be given a reaction, and it will say calculate the energy for this reaction. And so to do this, we're going to be given table 20.3, and what we're going to find is we're going to find our delta M, our change in mass. So we will find delta M, which is your mass of products minus the mass of reactants. All right, so you will look on your chart, except the only thing that is going to be listed correctly on your chart, well, none of these are going to be listed correctly, but you can say, you will know that a H11 is a proton. So you can simply use the mass of a proton, or you take the mass of H11 and subtract one electron. All right, so your choice, that one, you have a choice. I would pick proton and not subtract the electron. The other ones, you don't have a choice. They did not give the mass of a deuteron. All right, so they did give the mass of hydrogen, the element hydrogen 2,1 with the electron. And so you've got to subtract the one electron to get the mass of your deuteron. You've got to subtract 2 electrons to get the mass of your helium 3,2. You have to subtract 2 electrons to get your mass of your helium 4,2. All right, so, or as I'm looking at this, notice that we are subtracting the mass of 3 electrons on the left, and we are subtracting the mass of 3 electrons, so don't pick mass of proton here, pick the mass of hydrogen, and you're subtracting 1 electron here. All right, and so when you take 3 electrons and you subtract 3 electrons, you have not done anything in terms of changing the mass. So if you just take the numbers off of the table, making sure that you're using the hydrogen number, you do not have to subtract the electrons because it would work out. You had 3 electrons extra here, you had 3 electrons extra here. They subtracted themselves out in this reaction. All right, but if you want the actual nuclear mass, you would have to subtract the electrons that are on that table. All right, so you're going to have a nucleus, all right, per nucleus or nuclei. All right, so you have the nucleus. That's the protons and electrons. Now, that's protons and neutrons in the nucleus. All right, now a nucleon, these are members of the nucleus. So a nucleon is your protons plus your neutrons. All right, so you have, you're going to have things that are going to have energy per nuclei, and you're going to have energies per nucleon. And so that would then be per number of protons and neutrons. All right, so again, you can see, let's see what they have done. All right, so they took their helium 4,2 and they got their mass. They subtracted the 2 electrons, and so they used the 0.001520 for the helium. So since they did that, they have to use the mass of a proton, not the mass of H11. They also had to subtract 2 electrons from this mass, and they also had to subtract an electron to get that mass. So let's see how good my memory is. This is a 2.01345, 2.01345, 2.01345, 2.01345. So they did. So they subtracted the electron. All right. So this would be an interesting exercise to do this same problem. Do not change any of the numbers. Take them right off of table 20.3. Take the number for H21, He32, He42, H11, not proton, H11, and then you do the products minus reactants. and you should get the exact same answer. So if you add up that there are 3 electrons on this side and 3 electrons on that side, the mass has an extra 3 electrons. The mass has an extra 3 electrons. You subtract 3 electrons from 3 electrons, you have an effect of 0. So instead of going through all the trouble to subtract an electron, subtract 2 electrons, subtract 2 electrons, this one you wouldn't have to. They give you the proton. If you know you have the same number of electrons on both sides and they will cancel themselves out, you can just go with the numbers off of the table. But you should know that that's what you're doing. All right. So this is our delta M in AMU. I never work in AMU. I always work in grams per mole. So I have grams per mole. I also have my equation. That is delta E is equal to delta MC squared. And I also know that this is going to be in joules. And the key now that you must know about joules is that the mass is kilograms. And then you have meters per second, and you're going to square it. So a joule is a kilogram meter squared per second squared. So you're not going to put in a number that has grams. You have to convert this number to kilograms. So you have 1,000 grams in a kilogram. And so you have to divide that number by 1,000 in order to get that into kilograms. Once it's in kilograms, then you can put it into your E is equal to MC squared equation. All right, so when you divide that by 1,000 to get it into kilograms, you have your number here. All right, so now you have it in kilograms, and then your speed of light, that's a constant, will be given. You square it. All right, and so you have, and of course your mass loss was negative, and so this is an exothermic reaction. It is giving off energy. All right, and so this is then, so this was in AMUs, which was grams per mole. We converted it to kilograms, kilograms per mole. This is in joules per mole. All right, and so when we look at the reaction, it is for 1 mole of H21, 1 mole of He32, 1 mole He42, 1 mole H11. So it is per mole, depending on which of those you're asking for, but all of those are 1 mole. So that is in joules per mole. All right, so now we're going to convert the units from joules per mole into MeV. And we can go per mole, or we can go MeV per nuclei. All right, so since we have it in joules and we want it in MeV, we have to be given a conversion factor. We already know the conversion factor to get out of moles and get into nuclei. That is Avogadro's number. All right, so that is 6.022 times 10 to the 23rd nuclei per mole. So we can easily go to nuclei, and the MeV calculation, all right, is 1 MeV. This will be given. You don't have to memorize this. 1 mega electron volt, MeV, mega electron volt. 1.602 times 10 to the minus 13 joules. All right, so that is going to be given. So when we had our number, let's go back here. So we can do everything with this number here. So we have a negative 1.762 times 10 to the 12th joules per mole. If we wanted to get it in joules per nuclei, we have 6.022 times 10 to the 23rd nuclei per mole. All right, and so that's how we would get it into joules per nuclei. They do something ridiculous. Whatever, if you like their stuff, fine. I simply have this in joules per mole, then I convert it to joules per nuclei. When you divide that, you get this same exact number that they get, but they do it in a different way. All right, so this is joules per nuclei. All right, again, it's still negative because we just divided our joules per mole by Avogadro's number. All right, and so then to get it to MeV, now this one, okay, so this is MeV, and then I would always keep my per, what am I, got this, this is per nuclei. All right, and if they would say, yeah, if it was like, so for your He42, all right, so if they wanted it per alpha particle, so helium-42, so that is per helium-42 nuclei. But if they wanted it per nucleon of helium-42, there are 4 nucleons in one He42 nuclei. All right, because a nucleon is the number of protons plus the number of neutrons. All right, so that's your mass number, protons plus neutrons. That is called nucleons. So if we were just converting it to nucleons of He, we would have to then have 4 nucleons per 1 nuclei. And so you would then have your number, negative 18.26 MeV per nuclei. All right, and so you have 1 nuclei, which would cancel your nuclei, is 4 nucleons. All right, so you would have to then take your negative 18.26 divided by 4, and now you would have your MeVs per nucleon. So some of the problems in the book will ask it per nuclei, some per nucleon, some per mole. All right, so you'll have to know how to go from joules per mole to joules per nuclei to joules per nucleon. And whether it's joules or MeV, again, the conversion of joules and MeV, that is going to be given. You don't have to memorize that conversion. All right, a binding energy and a mass defect. All right, here is when you have your binding energy, energy to break a nucleus into individual protons and neutrons. So a very simple one would be the one we just did, He42. So we have a helium nucleus, and it would be the energy required to get that into 2 protons and 2 neutrons. All right, and so you would have your mass defect. When you got this off of the chart, you would have your mass defect. All right, so anytime you are taking a nuclei and converting it into its nucleons, so into its protons and its neutrons, that is called a nuclear binding energy. And the mass difference has a special name. It is called the mass defect. Whenever a nucleus goes to its nucleons. All right, the most stable nuclei that will not undergo binding is when you are at the 50 area. So a iron 56 is not going to undergo fusion. Fusion is when 2 smaller things combine to make a bigger thing, getting larger, and it will not undergo fission, which will go to smaller things. And so once you're at your highest binding energy, you're going to stay there, not do fusion, not do fission. All right, nuclear fission, you need to know that is a nuclear reaction where you're going to have a big thing going into smaller particles. All right, and it's also going to give off a number of neutrons plus a lot of energy. All right, you cannot predict your products. If I want a product, I can give you the other ones and have one missing. That's it. All right, because when you have uranium-235, which is our nuclear fission fuel, and we hit it with a neutron, we have 3 different modes that it can go by. You do not have to know those. You do have to know that they give off a lot of energy, and they give off a lot of neutrons. And then fusion is when you take two smaller things and make a bigger thing. And this is the energy of the stars and the sun. Fusion does not produce a lot of radioactive waste. However, we are not able to we're not able to get to a high enough temperature in order to do fusion. It requires a plasma temperature, which is 100 million degrees Celsius. We cannot reach that temperature. So we cannot do fusion on Earth, at least not at this point. But fission we can do, and this is our nuclear power plant. So you have to have your control rods, and what the control rods do is they absorb neutrons because it's a chain reaction. And if this reaction gets out of hand, as you see in this equation, you have uranium-235. One time it gives off a lot of energy and 3 neutrons, and now 3 times as much energy, and now 12 times. Okay, this heat builds up, and then you'll have a way too hot nuclear meltdown. You'll have Chernobyl, where you have to abandon it for years and years and years and years and forever, because it's still very radioactive there. All right, that is the end of chapter 20. We're going to review for the next 2 days.